Hello everybody and welcome back to another Algebra 1 video. Today we will be continuing with lesson 4.4 and its extension on solving special systems of equations. In our previous 3 videos we learned 3 different methods on how to solve a system of linear equations, the first being graphing on a coordinate plane, second was the substitution method, and the third was the elimination method. If you haven't yet, make sure to check those out on my channel, or I will also link them down below in the description box. For today's video, we won't be learning anything new. We'll just be using all 3 methods and applying them to different problems. So let's go ahead and get started by first reviewing the solutions of systems of linear equations. Remember that a system can have 3 different possibilities for its solution. The first being one solution, and if you look at this on a coordinate plane, it would be represented by this point of intersection between the 2 lines, and that point of intersection, or the ordered pair, would be the solution of the system. Secondly, we have no solution, and if you look at it on a coordinate plane, you'd see that it has no point of intersection. The lines are actually parallel. So, since there is no point of intersection, there will never be a solution for that system. And lastly, we have infinitely many solutions. On a coordinate plane, it would just look like one graph because whenever you have a system that contains basically the same equation or the same line, it will have infinitely many solutions because all the points that fall on that line will satisfy the system. This is just a quick review that we learned in lesson 4.1. And now we can go ahead and go into the examples. We're going to solve this system. The first equation is y equals 3x plus 1. And the second equation is y equals to 3x minus 5. Now you can really just apply any method that you'd like to solve this system, but for this example I'm going to solve this by graphing. So first, let's have our coordinate plane, and remember that we like to graph in slope-intercept form, which is y equals mx plus b. And m will equal to your slope, whereas b is your y-intercept, or where your line crosses the y-axis. Conveniently, both of these equations are already put into our slope-intercept form, so we can just graph them. So for equation 1, our y-intercept, or b, is positive 1. Make sure you're looking at what the signs are in front of your intercepts and values. So I'll go ahead and plot 1 on the y-axis, and we know that our slope is positive 3. Whenever you have a whole number, you can just assume that it's over 1. So remember that slope is rise over run, and since our slope is positive, you're going to go up 3 units and then run 1 unit to the right. So that would be your second point. And remember that you only need a minimum of 2 points to graph a linear equation. However, you can always do more if you'd like. So I'll go ahead and connect those 2 points with a line. And now that I've graphed our first equation, we can move on to the second one. We have y equals 3x minus 5. First, graph your y-intercept, which is negative 5. That would be right here on the coordinate plane. And once again, our slope is positive 3 over 1. So you're going to rise 3 units and then run 1 unit to the right. And you can do more points if you'd like once again, but 2 is the minimum. And now that you've plotted your points, you can connect them with a line. Now looking at our graph, we see that we have 2 parallel lines, and if you remember from the previous slide, whenever you have 2 parallel lines, it indicates that there is no solution. This is because there is never a point of intersection, since parallel lines will never intersect. And actually, if you recall from chapter 2, you could have already told that they were parallel given that they have the same slope but have different y-intercepts. So for this system, we have no solution. Now we have the exact same system from the previous problem, except now we're going to apply a different method, in this case substitution. Now remember, during substitution, your purpose is to substitute one of the equations into the other equation. The way you want to do this is you want to set one of the equations to either an isolated x or y value. Conveniently, both of these equations are already put or set to our isolated y value, so really we can just substitute one of them into the other. So how this would look like is we have y equals 3x plus 1. We also have y equals 3x minus 5. I'm going to take 3x minus 5, and since it's set to y, I'm going to substitute it into the y value of my other equation. You could also substitute 3x plus 1 for y into this equation, but it just depends on preference. So once you do that, you can go ahead and rewrite your equation, which gives you 3x minus 5 equals to 3x plus 1. And now you can solve for your x value. First, I'm going to subtract 3x from both sides. And notice here that 3x actually cancels. So bringing down your remaining terms, you get negative 5 equals to positive 1. Now whenever you have a statement like this where the numbers are just set to one another, you just have to evaluate whether it's true. We know that negative 5 does not equal to positive 1, so this system has no solution. And notice how we still get the same answer whenever we use substitution or graphing. So the method doesn't affect your solution. You'll always get the same answer every single time as long as you execute it correctly. Here we have another problem. We have that the perimeter of the rectangle A is 36 units. The perimeter of the rectangle B is 108 units. We're going to write and solve a system of linear equations to find the values of x and y. So we know that rectangle A has a perimeter of 36 units. So I'll just go ahead and indicate that there. And recall that perimeter is the sum of all the sides. So this side that measures 4y will have this other side measuring 4y as well, since they are the same length. And same goes for this side length. They would both be 2x since they are equal to one another. As for rectangle B, the perimeter equals to 108 units. And I'll just go ahead and indicate that this side length is 6x and this side length is 12y. Now we're trying to find the values of x and y, so let's go ahead and make a system of linear equations. The way you would format this is you would make one equation for the perimeter of rectangle A, and the other equation can be the perimeter of rectangle B. So for rectangle A, again, perimeter is the sum of all the sides. So we would have 2x plus 2x, and then plus 4y, and that would equal to your perimeter, which we said was 36. Now you can actually combine like terms. 2x plus 2x would just give you 4x, and as for 4y plus 4y, that would give you 8y. And then set that to 36, and here is your first equation. Do the same for rectangle B. You would add all your lengths, side lengths, which would be 12y plus 12y, and then plus 6x, and then plus 6x again, and set that to your perimeter, which was 108. Again, you can combine like terms, so 12y plus 12y would just equal to 24y, and then 6x plus 6x would just equal to 12x. And again, set that to 108. So here are your two equations that make up your system of equations. Now that you have a system, you can go ahead and solve for x and y. Method 1, I'm going to use graphing. So we have our coordinate plane here and then our system. Again, we always want to graph in slope-intercept form, which is y equals to mx plus b. First, you want to subtract 4x from both sides. And the reason why you want to do this is because your ultimate goal is to isolate your y value. And now that you've subtracted 4x from both sides, you can divide everything by 8, and that would give you y equals to negative 1/2 x. Now I just rearranged it so that we can fit with the y equals mx plus b. And I got negative 1/2 from negative 4 over 8. Negative 4 over 8 would simplify or reduce to 1/2. And then 36 divided by 8 is actually 4.5. So I would just put that as 4.5. So your first equation rewritten in slope-intercept form would be y equals negative 1/2 x plus 4.5. You can do the same for our second equation. Again, y equals mx plus b. Isolate y by first subtracting both sides by 12x, and that would give you 24y equals to 12x, or negative 12x, plus 108, and then you would divide both sides by 24 to isolate y, and then simplify. Y would equal to negative 12x over 24. That would simplify to negative 1/2 x. And then 108 plus 20 over 24 is 4.5. And here is your your rewritten equation for 12x plus 24y equals 108. Now looking at our two rewritten equations, notice that they are actually the same. And whenever you have the same line or the same equation, you know that this is going to be infinitely many solutions, because any point that falls on the line will satisfy both equations. So since we really only have one line, we just have to graph one line on our coordinate plane. We're going to first plot our y-intercept, which is positive 4.5. So that would just be the halfway point between 4 and 5 on the y-axis. And looking at our slope, we see that it's actually negative. So rather than going up 1 unit, we're going to go down 1 unit, but you're still going to run 2 units to the right. So 1 unit would be this halfway point plus this halfway point, and then 2 units to the right, and there is your second point. So you can go ahead and connect these 2 points to get your line. And again, we're only plotting or graphing one line on our coordinate plane, since we have the same exact line for our system. And here's how it would look on a coordinate plane. Now we are going to solve the exact same system, except we're going to be using another method. For this method, we're going to be using elimination. And remember that with elimination, your purpose is to eliminate one of the like terms. So either you would have positive 4x and positive 12x, and you would eliminate those two, or you could also eliminate positive 8y and positive 24y. The way you would go about this is that you need to get both of the terms to be the same values. So they need to have the same variable, and they also need to have the same coefficient. So for example, 4x and 12x would both need to be 12x, and you would multiply one of those, or you would multiply the equation containing 4x by 3. And also, one of your values has to be negative and the other has to be positive in order for them to cancel. So in the case of if you were to try to eliminate these terms, 4x and 12x, you would multiply the entire equation by -3. Now that's just an example. Let's go ahead and start solving for our values. I'm going to go ahead and multiply 4x plus 8x equals 36 by -3. And why I'm doing this is to eliminate this positive 12x in the other equation. And if I were to multiply the entire equation by -3, make sure again that whenever you're using elimination, you're multiplying the entire thing. You would get -12x minus 24y equals to -108. And now you can go ahead and write your other equation. And now you can do your elimination. -12x and positive 12x will cancel. Notice here that -24y and positive 24y also cancel. And so does -108 and positive 108. So the final equation you get is just 0 equals to 0. And again, when you get something like this, where a number is set to another number, you just have to evaluate whether it is true. 0 is equal to 0, so we know that this system has infinitely many solutions. This is because the equation 0 equals 0 is always true. And notice that this answer, again, is the exact same as what we got when we graphed it. Now we will be moving into new material for this lesson. We're going to be solving equations using graphs, particularly to solve the equation in this format, ax plus b equals to cx plus d. And actually, it's pretty simple to solve these. You're just going to write two linear equations, and they're actually already given in this format. You just have to break them apart, so you would make one equation set to ax plus b, and the other equation would be set to cx plus d. And that's shown right here. And once you've broken down that equation into two linear equations, you can just go ahead and graph it on a coordinate plane. It's already set in y equals mx plus b, or slope-intercept form, so it's pretty simple to graph. And actually in this case, it's just the x value of the solution of the system of linear equations that is going to be the solution of our equation ax plus b equals cx plus d. So whenever you have a linear equation set in this form, you're not looking for x and y, you just have to state the x value. Let's go ahead and do a few examples. First, we have x minus 2 equals to -1/2x plus 1. This is in our ax plus b equals to cx plus d form. And remember that we're just breaking it down into two equations. So make one equation that is set to x minus 2. The other equation will be set to -1/2x plus 1. So we would have y equals to x minus 2 and y equals to 1/2x plus 1. And now that you have your two equations, just graph them on a coordinate plane. these are set into our slope-intercept form. We have our slope, and we also have our y-intercept, so I'll use that method to graph. For y equals x minus 2, our y-intercept is -2, so graph that on your y-axis, and your slope is just +1. And whenever you just see x, just always visualize a coefficient of 1 in front of it. In math, we don't usually disclose a 1 in front of a variable, so always just visualize that in your head. And if you have a slope of 1, it would just be 1 over 1, and it is positive, so you would just go up 1 unit and run 1 unit to the right, and you can do that a few times if you'd like. But again, you just need 2 points, and once you've plotted your points, connect them with a line. Now that you've plotted your first line, you can move on to your second one. We have y equals to -1/2 x plus 1. Our y-intercept is actually +1. So I would plot +1 on our plane. And now look at our slope. We have a negative slope. So rather than going up 1 unit, you're going to go down 1 unit. And this is 1 over 2. So you would go down 1 unit and then run 2 times to the right. And I recommend that you continue to draw points until you hit your other line. So in this case, with just 1 other point, we were already able to hit y equals x minus 2. So I'll go ahead and connect my 2 points with a line. And now that you've plotted all your points and connected your lines, you can go ahead and look at the point of intersection. Our point of intersection here is 2, 0. And remember that for these types of problems, you only need the x value for your solution. So in this case, we would have x equals 2 for our solution. Here is another example. We're going to solve x plus 3 equals to 1/2 x plus 1 using a graph. This is in ax plus b equals cx plus d form, so go ahead and break these down into 2 different equations. So one will be y equals x plus 3, the other will be y equals 1/2 x plus 1. So here are our 2 equations. And since they are in slope-intercept form, we can go ahead and start graphing them. For y equals x plus 3, our y-intercept is +3. So plot 3 on the y-axis, and now we have a slope of 1 over 1. And this is +1, so you would rise 1 unit and then run 1 unit to the right. And you can do that a few more times. Once you've plotted your points, go ahead and connect them with a line. Now that we've plotted our first line, we can move on to y equals 1/2 x plus 1. +1 is our y-intercept, so I'm going to plot that on our plane. And as far as slope, we have 1 over 2. It is positive, so we're going to rise 1 unit and run 2 units to the right. So rise 1 unit and then run 2 units to the right. Rise 1 unit and run 2 units to the right. However, see, we haven't yet intercepted our other line, so I'll go ahead and go down 1 unit and 2 units to the left, and then down 1 unit and 2 units to the left until I have hit my other line. You can see here that we've already made a point of interception. So now that we've plotted all our points, we can go ahead and connect them. And let's look at our point of intersection. Our point of intersection is -4, -1. And again, we only need our x value for a solution. So our x value is -4, and our final solution would be x equals 2, -4. Here is a word problem. We have that plant A grows 0.6 inches per month, and plant B grows twice as fast. We're going to use this model right here, and we're going to write an equation. This equation is going to be used to solve for after how many months are the plants going to be the same height. So I'm going to go ahead and lay out a equation format. First, I want to multiply my growth rate by the unknown months that it's going to take for the plants to be the same height. So that would be growth rate times month x, and that would be plus our original height. And then I'm going to set that equal to the growth rate of the other plant times the months x, and then add the original height of the other plant. And notice here that we actually have it in our ax plus b equals to cx plus d form. So we're going to be applying that concept to a real life situation. And if I were to do this, our growth rate for plant A is 0.6, and then times our unknown amount of months, which is x, plus the original height of plant A, which is given to us to be 12 inches. And here is your first portion of your equation. Then set that equal to the portion of the equation representing plant B. Our growth rate for plant B is twice as fast as plant A's, so 0.6 times 2, which would represent the double the rate of plant A, would be 1.2. So that's how we got our 1.2 in this equation. And then multiply that by your unknown numbers of months, which is x, plus the original height, which was 9. And here is your final equation in ax plus b equals cx plus d form. 0.6x plus 12 equals to 1.2x plus 9. And now we can actually graph this on a coordinate plane. Now it is a little bit tricky since we are in decimals. However, we can try our best to graph this. For our first equation, we're going to graph our y-intercept, which is positive 12. So that would be located right there. And then we can make 0.6 into 6 over 10, which equals to 3 over 5. So whenever you're given a slope of a linear equation in decimals, I always recommend to put it in fraction form. So you would rise 3 units and run 5. That would be the other point. Again, you only need a minimum of 2 points, so you can connect your first line. And as for y equals 1.2x plus 9, our y-intercept is positive 9, so I'm going to plot 9 on our y-axis, and 1.2 as a fraction, you can actually make this into 12 over 10, and 12 over 10 just simplifies to 6 over 5, so your slope would be positive 6 over 5, and you would rise 6 units and run 5. So from your 9 here, rise 6 units, and that would be right here, and then run 5. That would be at this point. And notice here that it intercepts right into your other line. So you can go ahead and draw your line through your 2 points and analyze your point of intersection. So our point of intersection is going to be 5, 15, And remember, we were in ax plus b equals cx plus d form, and the original problem was only looking for how many months it would take for the plants to be the same height, and that was represented by the value x. So your final solution would just be x equals 5. And in this case, the y value of our ordered pair would actually represent the height of our plants. So the plants are both going to be 15 inches tall after 5 months. That is it for today's video. Thank you so much for watching. As always, all information regarding tutoring, additional practice, and lesson plan requests will be linked down below in the description box. If you ever have any general questions about the lessons, please feel free to reach out to me at kaylin.david24@gmail.com. I hope to see you in the next video.